BGP, or Border Gateway Protocol. What absolutely massive protocol this truly is. Not only does it make the whole internet work because it's in the data centers, it's in the service provider networks, it's in enterprise networks, it's even the protocol that runs, it's the only protocol that runs that in between networks themselves. But there's a lot that you can do with BGP. Regardless of vendor, there's lots of configurations and policies and attributes that we can actually manipulate and modify and change to tailor BGP in our actual network. And in this video, what we're going to be going through is what are the BGP path attributes. And this is a huge topic for BGP because regardless of vendor, any router has to decide how it's going to get to an end destination. And those BGP path attributes are absolutely important and essential to allow that router to make that best routing decision possible. And those questions of what are those path attributes, how can we influence them, what are they in terms of order in the Juniper Junos world, are those type of questions that we're going to go through in this video. But we're also going to focus on the top two of those BGP path attributes. That's the local preference and AIGP. Not going to say any more than that right now. But if you like this video, please give it a like, and additionally, please subscribe to the channel so you can keep up to date with all the latest and greatest videos that I release weekly. Now, before we actually start going through the different type of BGP path attributes and the list, the criteria, it's important to understand initially that what BGP routers are doing when they go through this attribute list is looking for a tiebreaker. There's a huge list of attributes that a BGP router will go through, and that router is going from first one to the second to the third to the fourth until eventually it finds that tiebreaker. Now, there's different lists, there's different attributes, and of course different ways we can manipulate them. But what that router is essentially doing is just waiting, checking, and deciding based on that attribute type, is this the more preferred path? Is this the more preferred route to get to that given destination? And if it is, that will be the tiebreaker, and then it won't move on to the other steps in that BGP path selection process. Now, the story actually is that when BGP was first defined of the many standards and draft standards that have come out over all these years, that every vendor was pretty much treating BGP proprietary. Everyone was doing their own thing. And so the standards, the ITF, the ITU, wherever it's actually defined, they came out with a list of standards which defined those BGP path attributes. Now, obviously, you can go away and read those attributes, but let's face it, that's just going to be... So obviously, we're not going to do that, but first, let's just start off with those different attribute types. And first, there is the well-known type of BGP path attribute, but there's also a second one, which is the optional attribution. Now, what I'm going to do is I'm actually just going to break this into two different parts, or four squares as such, if you want to think of it that way, because there's actually two different flavors of these BGP path attribute types. We've got the vendor, and also we've got when they are sent. Now, if you've seen my video that I've done on the BGP message types, if you haven't seen that video, just check out this link, it's all explained there. There's different type of BGP messages. There's the notification, there's the update, there's the hello, there's the keep alive. Now, specifically for these, we are referring to the update message, because the update message, which refers to all that network layer reachability information, i.e. all the networks that's contained within that update itself, this contains those path attributes. But here we're looking at, well, when are these actually sent? Now, well-known has two different variants, as does optional. Specifically for well-known, there's mandatory and also there's discretionary. So let's just start off. First, well-known. What this means for well-known is in the update message, this has to be supported by every single vendor. Doesn't matter if it's Juniper, doesn't matter if it's Cisco, doesn't matter if it's Fortinet, Extreme, Aruba, and the list goes on and on and on. Anyone that supports BGP, when there's an update message that is received on an interface, whatever that interface may be, if that path attribute is well known, that vendor has to support it. There's no ifs, there's no buts. You have to support it. But then there's these, well, when are they actually sent? So mandatory means in every update message, those path attributes have to be there. They have to be defined. And this is actually the one that's going to cause the main issues when it comes to the BGP peering. Because if those messages are not in that update message, in every update message, then that peering between those BGP speaking routers is actually going to break down. It's going to be terminated. The TCP is going to break, and there you go. The routing is just going to fail from a BGP perspective. So most of the issues you're going to see or experience, let's hope not, will be because you have got mandatory fields for those well-known path attributes which are actually missing. So mandatory means that has to be there for every single update message, and well-known just basically means every vendor has to support that. It's just a well-known path attribute at the end of the day. But what does discretionary mean? Discretionary is another way of just saying optional at the end of the day. So yes, it's well-known. Every vendor has to support these well-known BGP path attributes. And don't worry, I'm going to say what these attributes are and what type they are in just a few minutes. But the discretionary means that those attributes don't have to be in every single update message. Unlike the mandatory, which absolutely has to be there, otherwise the peering was just torn down. With discretionary, it's not really the case. It's not so strict. And then we actually move on to the optional type of BGP path attributes, and for this we've got transitive and non-transitive. Big word there to write out. I was almost running out of space. But what does this optional actually mean? Optional means that the vendor themselves don't have to actually support it. It's defined, but it's really more proprietary. So if we look at Cisco, for example, with their BGP, right at the top they've got wait. Now that is not a well-known, sorry all you Cisco gurus, but it is not a well-known BGP path attribute type. It is actually optional. Not all vendors have to support it. And more than likely, we're never going to support it. Otherwise, we would have done so by now. So optional just basically means that it can be there in those update messages, but not necessarily the vendors have to support it. But then we come down to transitive and non-transitive. Transitive basically means if a vendor, if a switch, if a Juniper router receives an update message with an optional type of BGP path attribute and it's transitive, it means we can forward it on to other BGP peers within the same autonomous system. Non-transitive basically means we are not going to forward it on to other routers. We are just going to keep it for ourselves. We're going to process it. We're going to do some kind of magic eye routing and update on those update messages themselves, but we aren't going to forward that type of message on. So that's just very briefly the different types of BGP path attributes, well-known, optional, and 2 different variants for each one. So what I've done is I've just put a little key down the bottom to actually just refer back to what are those type of BGP path attributes. So we've got well-known mandatory, well-known discretionary, optional transitive, and optional non-transitive. Now, when you do any type of Google in terms of what are the path attributes for BGP, you're going to see number 1 being something, but that's not actually technically correct, whatever that actually may say. The actual very first thing a router will look at is the preference, or in the Cisco world, you'd call that the administrative cost. So instead of writing out all the preferences for Junos, I thought I'd just grab a quick table, but you could see them all here. Now, obviously, we're not going to go through all these. That's not the intention because, again, you're going to fall asleep. But it's important to note out that if there is 2 routes or 2 options to get to the same network, say you've got one which goes over OSPF and one that goes over IBGP, just for example, if you look at the preference list, and I'll just change the color, but if we look at OSPF to actually BGP down here, you can see a massive difference. OSPF for internal routes has a cost of 10, whereas BGP has a cost of 170. Now this is of course different to the Cisco administrative distance cost. I think BGP in Cisco is 20 or something, whereas you can see that is significantly different in Junos, obviously with different vendors at the end of the day. But the point actually is that the router will decide what routing table and what path and egress interface, etc., to send those packets out of first based off the preference of the routing table. So obviously lower the preference means that that routing protocol is more preferable. OSPF is always going to win in the Junos world over BGP. So let's now look at the list of those path attributes in the Junos world from the top to the actual bottom. Now, what is the first one after the preference? Now, the first one is actually next hop. That is really important. And by the way, this is a well-known mandatory type attribute. This is really important because if we remember back to the IBGP type configuration, if you haven't seen that video, here's the link. But if that next hop is not resolved, if it's not reachable, it's not going to go from that BGP rib in table to the actual main routing table itself. That next hop has to be valid. What is the one that's actually after the next hop? So say the next hop is valid, it is reachable. What comes next? And sorry everyone from Cisco, but the second attribute in the Junos world is not wait. Not that I looked it up. But what comes second in the Junos world isn't wait, because that is optional at the end of the day. Not all vendors have to support it. What comes second in the Junos world is local preference, which is a well-known discretionary type of attribute. Again, what that means is that when it is sent, it doesn't have to be sent in every update messages, but when it is sent, those vendors have to know how to deal and handle and process and interrogate that information that is contained in the update message, so it has to be supported. And what local preference actually is it's the ability of an autonomous system for routers inside the autonomous system to have, for example, we're going to see this in the lab, to have different routes, different paths to get to the same destination, and we want to communicate internally, i.e. locally, to that same autonomous system. How do we want to actually get to that destination? So do you want to prefer one path or the other path? And think of it as load balancing. In the Junos world, the default is 100. Now, higher the value, the more preferred it is. So what you can actually do, and what we're going to do in the lab, is actually define some networks to be preferred over one egress router, one router facing one service provider network, and other networks being preferred to take a different route, via a different router and via a different service provider network. So it allows us to do load balancing, allows us to locally prefer one path over another, but to get to that same destination at the end of the day. The third one is AIGP, and this is the other type of path attribute we're going to go through in the lab in a few minutes time. And this is an optional transitive type of attribute. Now, AIGP stands for Accumulated Interior Gateway Protocol. Now, what does it actually do? The name kind of gives it away. It's accumulation of the Interior Gateway Protocol's costs. So whether it be using OSPF or ISIS, doesn't matter. They all have their different type of metrics, a different type of algorithms to derive some kind of cost. And what the AIGP is basically doing is it's adding up all the accumulation of all the autonomous systems costs inside the different networks from point A to point B, from source to destination, across all those networks, and it's adding up all those costs together to really understand what is the overall or total cost from an IGP perspective to get from that source to that destination from A to B. The fourth one in the Junos world is AS Path. Now, I've already sort of like discussed this in previous videos, and what AS Path basically does is it allows two functions, two purposes in my opinion. One is loop prevention. When we've got update messages coming through which detail the path attributes for all the network layer reachability information, i.e. the different networks, what it's detailing is all the different autonomous systems that those packets have traversed through, have gone through, and thus you can actually trace to get from wherever your network is to that destination, how many networks do those packets have to go through. Now, it's a loop prevention because with AS Path, if your autonomous system is say 65100, which we're using in the lab, if the BGP routers see their own autonomous system, i.e. 65100, in the AS path attribute list, and they know, oh, hang on, these packets have already gone through my network, but now they're back again. So there's a loop somewhere, something's not working, and immediately they're just going to ditch those packets. The other function of AS path is thus to determine what is the shortest path, because BGP is a path vector protocol at the end of the day, is to determine what is the shortest path to get to that destination, i.e. the fewer autonomous systems in that AS path list, the more preferred it actually is. Now, in any environment, in any vendor, you can add AS numbers, you can append and prepend AS numbers to that list to, again, filter and decide or influence, manipulate on how those routers pick one route over another. And the fifth item in the Junos BGP world is origin. What origin means is what it basically sounds like. What is the origin of this network that's been advertised, of this prefix that's been advertised into BGP? Now, the way it goes is that I is more preferred over E. E is more preferred over the question mark, which is what that's meant to be there. But I stands for internal. It's learned internal to our own network, or it's been learned internal to whoever's network is actually advertising that. E stands for external. Now this pretty much isn't seen these days because, well, I actually don't know. I've never seen E in an origin code, so because eBGP is the only really protocol out there, so for me this is pretty much died. It's just gone, so you're never really going to see E. I'm not going to waste any more time on that. But question mark means something else. In the Cisco world, you'd see a question mark when you've got a BGP router which is exporting some kind of internal gateway protocol like OSPF or some kind of static route, and they're exporting those routes into BGP. Now in the Junos world, that's not the same case, and it does make sense, because in the Junos world, when we export those protocols, those networks learned by those protocols from OSPF, from ISIS or whatever into BGP, we actually know where they're coming from, and that's done within the autonomous system itself, wherever that autonomous system may be. So it's still internal. You can, in the Junos world, however, influence and manipulate those path attributes to move away from internal to actually be a question mark. Because again, we have to remember that the path attribute is basically a decision list where we go from 1 to 2, 2 to 3, 3 to 4, 4 to 5, and it keeps going down and down and down. And what this basically allows is a tied decision making process. Right at the top, just as a quick summary, is the next hop actually resolvable? Is it reachable? Yes. Well, let's move on to the next step. What's the local preference? Am I going to prefer this route to that router, or this route to that router to get to the same destination? If they've both got the same default value of 100 or whatever value it may be, they'll move on to the third step, ARGP. If it's enabled, it's a pretty niche use case. But really, number 4 is where a lot of decisions are actually made, because here we're going to see what is the path list to get to that destination. But if both paths are the same in terms of length and they're not in some kind of loop, then look at the origin. Like, how trustworthy is that update message? If it's internal, that's more trustworthy than a question mark at the end of the day. So this is basically a decision making process. It's a tie, and if there's a tie, it will move on to the next step, and the next step. If there's not a tie, then it will stop at whatever step it actually is and base its routing decision on that actual attribute itself. Next in the list in the Junos world is multi-exit discriminator, or MED for short. Now this is an optional non-transitive attribute. Just for refresh, what that means is that not all vendors have to support it. It's optional at the end of the day. But if it is sent in an update message, if the vendor supports it, it's non-transitive. So only that router is going to process it. It's not going to forward it onto any other routers in that same autonomous system. What is MED, or multi-exit discriminator? I like to think of it as the reverse of local preference. Local preference, we were advertising internally, locally to our own autonomous system, what the preferred path is to get to that destination. Multi-exit discriminator is the flip side of that. We are advertising to our peers, our external peers, how they should send traffic to us. So it's a form of traffic engineering. We can actually tell eBGP peers, based on cost of the multi-exit discriminator, you need to send your networks which are destined to somewhere in my network, in my autonomous system. You need to send it to this router or that router, to this interface or that interface. It's traffic engineering. For me, maybe you can see the logic is vice versa to local preference. And just to save time, what I've just done is actually put on all the other types of path attributes in the Junos world for BGP. But always remember, this is a decision-making process where we're looking for a tie. And if there's a tie, we move on to the next one and the next one and the next one till eventually there is a tie breaker. So after multi-exit discriminator, we then have eBGP versus iBGP. So this isn't actually well defined, but basically this comes down to the nature of iBGP, route reflectors which are required on the next hop itself. So how trustworthy again is that actual source? And then we move on to IGP. So typically, how trustworthy is the interior gateway protocol? Is it learned via static routing? Is it learned via OSPF? Is it learned via ISIS? And so on and so forth. Then we start moving on to what is the oldest path. Typically, the path that is in the routing table the longest is the one that is more preferred because it's been around longer, it's more trustworthy. And then we move on to router ID. The higher the router ID, the more preferred that will be. Then we move on to cluster list or community list. So this is a topic we're going to be covering in quite great detail in the future, but just know that higher the cluster list, the more preferred it is. And then finally, right at the end, there is the IP address. Again, guess what? Higher the IP address, the more preferred it will actually be. But at all points, what that BGP router is looking for is that tie breaker. First, as a quick summary, is the next hop. Is it actually reachable? Is it resolvable? If it's not resolvable, it's not even going to be in the routing table. It won't pass the initial checks. Second, and I've just changed the color just to be a bit different, is local preference. If there is more than one path to get to that destination, the same destination, we can influence locally to the autonomous system what is that local preference for other BGP speaking routers to take, i.e. where do we want them to route their packets through. Higher the value, the more preferred it actually is. But if all values are the same, it then moves on to AIGP. Very unique niche case here, more for service providers where they have a huge autonomous system and multiple autonomous systems within that autonomous system. And then we move on to the fourth one. Here, this is really the main tiebreaker. AS path, looking for the shortest path, the shortest list of autonomous systems to get to that destination. And it keeps going on and on and on and on and so on and so forth till we get to that tie breaker. So that is the BGP path attribute types and the list itself in the Junos world. And now what we're going to do is actually go onto a lab and see what is configured and how can we actually start influencing routers' decision based on local preference. And so here's the lab that we're going to be using to do the local preference configuration and the AIGP. And I just want to give a quick overview so you know what it is you're actually going to be seeing when I jump onto the Junos CLI. Now, a lot of the configuration, pretty much all the configuration we're going to be doing is on this router here. That is router R10. And everything is pretty much set up. We've got our eBGP configuration configured between our autonomous systems. And we've also got iBGP running throughout every single autonomous system itself. And obviously down here in Service Provider 2 and probably not so much in Service Provider 3 because it's a very small network. But what you need to know is that in the Enterprise B network, what I've done on these 4 routers is I've actually configured a static route. And what this static route basically is on R18, R19, R20 and R21, I've configured something like 18.18.18.18/32 for R18. R19 is 19.19.19.19.19/32. And obviously you can see where I'm going for R20 and R21. Those static routes are then exported into the BGP protocol, and they are automatically distributed, advertised over through the network into Enterprise A. So what we're going to see when we go onto router R10's routing tables, we're going to see not all four, because actually the router here R18 is not configured for this right now, so I told a little bit of a porky there. What you will see is the R20, the R21 and the R19's static address. The reason why I'm doing that is so it simulates that of loopback address, and also that we can have that round trip connectivity from Enterprise A all the way over to Enterprise B and obviously back again. Now, as I said during the introduction and on the last part of this video, with local preference, it is not something that is used to advertise a preference or value to external networks, to external autonomous systems. So R10 here and R5 up here, if we were to configure local preference on R5, it's not going to advertise to R1 and this router down here what its local preference is. That's just not going to happen. What they will do though, specifically for R10, is R10 will advertise up to R5, across to R6 and across to R11 what its local preference is, because that is the first step after next hop reachability. That is the first step in the BGP path attribute selection process. And of course, remember, in Junos, that local preference default value is 100. So all these routers, R10, etc., will have that default value of 100. Now, what I could do is define it to be, say, 101. And then all these routers would prefer router R10 to have that egress connection out into the network and essentially get all the way over to Enterprise B over here. My point there really is higher the value, the more preferred it actually is. So if you've got two routes, one has a local preference of 100 and the other has a local preference of 101, guess which one's going to win? It's going to be the higher value of 101. If there is a tie, meaning that both those local preference values are the same, guess what? It's going to move on to AIGP, the next step in that BGP path selection process. But the main thing to take away here is that local preference is advertised internally towards all routers within that same autonomous system. It's not something that's advertised to external networks, to external autonomous systems. And here's the command line interface of router R10. I'm just going to log in. And if I just do quickly a show route, what we can see, as I described, we've got R19, we've got R20, we've got R21. I did also say that R18, I've not really configured that, but it doesn't matter. So R10 can actually see all the way across the network to Enterprise B over here. You can see R19 and all the other routers minus R18 in Enterprise B. But what you can also see using the routing table is that for each one of these, we've actually got, if we just focus in on the 19/32, i.e. R19, we can actually see we've got two paths. One path is going up to router R5 because those networks, those routers, those static routes have been injected into BGP and advertised all the way through this service provider network over to this Enterprise A router R5. So R5 is aware of those as well. So right here it's saying to get to that network or to that host, we can go out of the GIGI 002 interface, i.e. up to router R5, or we can go out of the GIGI 000 interface, which is this interface here, over to service provider 2 and thus all the way across down here. So, and it's actually the same for all those routes there. We've got two different ways to get to that same destination. But how do you actually configure the local preference? How can we actually configure it to manipulate other routers to prefer this router or to prefer this router for specific destinations or networks, wherever those networks might be? It's actually very, very easy to configure. If I just go into configure, and there's two ways you can actually do this. If I go into edit protocols BGP and I want to select my group, internal AS65100, and if I just do a quick show, you can see all the previous configurations I've done. So it's internal, this is my local address here, I'm advertising next hop self, and here are my peer neighbors. Here are the neighbors with R5 R6 and R11. And if I just quickly do a run show BGP summary, and you can see all are in the established state, everything's working, everything's as it should be. But back to local preference, as I said, there's two ways you could actually do this. The very first way is to do set, if I hit question mark, note here, local preference. So we could define within the group the local preference value. So if I do local preference 101, do show, and now you can see just there for this entire group we have defined the local preference of 101. Now a word of caution here, we are doing that for the entire group. So these three neighbors, routers R5, R6 and R11, when they receive this update of R10 having a local preference of 101 for that entire group, all networks, all destinations, whatever they may be, R5, R6, R11 is just automatically going to prefer R10 and this egress interface to get out of the network, because we are doing this at the group level, which is going to impact all these neighbors here. Now that might be something you want to do. However, it might be something you do not want to do. Maybe you want this to be an active link, and maybe you just want this as a standby link. If that's the scenario, if that's the use case, fine, that will absolutely work. But what if you want active? Or what if this is a 10 gig link here and this is a 1 gig link here? Obviously, we don't want to saturate this link with all of Autonomous Systems A, Enterprise A's network traffic to get through to Enterprise B. It's just going to be saturated. Hence, we can use local preference to actually do some form of load balancing, where based on destinations, we could say some traffic's going to go this way and other traffic's going to go that way based on that destination of the network itself. And this is the second way we can actually configure local preference. Now to do this, we need to take an extra step in the configuration process. So what I'm going to do is I'm just going to go to the top, and we need to configure a policy statement. So I'm just going to do edit policy options, policy statement, and I'm just going to call it LP for local preference for short. Now we need to define a route filter. So first we need to say set term 1 or term 2 or just whatever name it may be. It doesn't have to be a number. I can actually just say term 18 or 19/32. So this is going to be for R19. So now I can actually say from route filter 19.19.19.19 exactly, and now I want to say then local preference. If I hit question mark, you can see we just want to apply a particular number, or we can even subtract from it actually. So then local preference, if I give this 101, and now if I do show, we can see we've gave it a name, we've identified specifically R19 from the route filter, and we've said specifically for this destination in this case, or it could be for a whole network, I want to give this local preference of 101. Now the next step in this process is to configure that into the BGP protocol. To do that, it is very straightforward, and what we need to do now is actually configure that policy statement of local preference to go into the BGP protocol. And to do that is very straightforward. If I just do top, and I'm just going to do set protocols BGP group internal, and now I could do this at the group level. So I could do export, and if I hit question mark, you can see there's the local preference there, or I could actually just do this for a particular neighbor. So if I enter in neighbor and say I want to do this to router R11, if I hit export and question mark, you could see the local preference there. So this allows granular control of your autonomous system, of your network through BGP and the local preference. I could define for the entire group, for all neighbors within that group, to prefer me, if I've got a higher local preference value, to prefer me as that egress router to get to that destination. Or I could do it for specific neighbors themselves. Either way, it's actually going to accomplish the same objective of manipulating the BGP Path Selection process and for us to do some form of load balancing. But what I'm going to do is I'm just going to do it at the group level, and if I do a quick show, and I forgot I'm not actually in the protocol itself, so the show brought up a bit of configuration there, but if I do show protocols BGP group internal, And what we can see is I've now configured that local preference. I probably just want to delete this as well, so I'm just going to delete that. And there you go, I deleted it. So now you can actually see that local preference is gone via this command here, and now I've only got that local preference. So if I do a commit on that now, and that is the configuration actually done. That is it. That's all you need to do for local preference manipulation on Junos devices. But in summary, what we have done is we've configured that 19/32 address, that destination, to have that value of 101, and therefore R5, and because we done it at the group level, R5, R6 and R11 is automatically going to prefer router R10 to get to that destination itself. We could also go on router R5 here and do the same for 20/32, i.e. R20, and maybe we wanted to set R21 to be preferred down here on router R10 as well. There's many ways you could go around it, of course, and if I actually had it configured, I could actually do the 18/32, i.e. R18, to be configured up here with a local preference of 101 as well. So therefore, for these networks here, for these destinations, all these routers would prefer and would choose to go via R5 to get to those destinations, whereas for these networks here, they're going to prefer to go down here. Hence, we can use local preference to do load balancing, and those are the two ways to configure local preference on Junos devices. So as you can see, very quick, very straightforward, not very complicated at all. And let's now move on to accumulated IGP, or Interior Gateway Protocol. And for me, the title, the name of AIGP really does give it away, because it's an accumulation of the Interior Gateway Protocol's metric. Now this is quite a niche and specific use case, and to actually show this, what I'm going to do is actually focus in on the service provider networks to try and explain where and why you'd actually use this. So say, just for example, that service provider 1, service provider 2 and service provider 3, they were all the same autonomous system. So if I just draw that out now in a great big box, that they were in the same autonomous system. So maybe these were different confederations, different clusters, but essentially this was one big service provider network, all with different autonomous systems within it. Now the idea of AIGP is that each of these autonomous systems, AS1, AS2, AS3, are all running their Interior Gateway Protocol. Now in this lab, on each one of these networks, that is OSPF. And if you've seen the videos that I've done on OSPF, here's a few links, you will know that the OSPF uses the shortest path first, or SPF algorithm, specifically the Dijkstra algorithm, to calculate what is the best path or best route to get to a destination based on, guess what, shortest path, i.e. the metrics of the interfaces themselves. And what we want to do with AIGP is essentially carry those metrics, those costs that's associated to that IGP, which in this case is OSPF, but it could be ISIS or other. It has to be the same metric in all the autonomous systems though for it to really make sense. It's going to carry that AIGP overall total metric throughout the network. And the idea here is thus. If we look at it from this router's perspective, you're going to have lots of routers connected to this. On here, you're going to have servers. That's my drawing for server. And up here, you're going to have routers as well, all connected to each other. And down here, guess what? You're going to have more routers and more servers, more hosts, etc. connected. The idea of AIGP is to calculate based on that OSPF or whatever that IGP metric is, what is the best path to get to that source, to that actual destination, i.e. from up the top here all the way down to the bottom here. As you can see in this actual example though, there's no real direct link between the different service provider networks, or the different AS1, AS2, AS3, and thus what you would typically have to have is a link between the different service provider networks, or the different autonomous system networks I should actually say, and the IGP metric is being carried over that eBGP peering because they're different autonomous systems at the end of the day. And that's really a big point there, is that we're using BGP to carry that interior gateway protocol's cost, its metric. And thus the service provider knows, based on its IGP metric, what is the best cost, what is the best route to get from that source down to that destination. Now AIGP is both built for eBGP and for iBGP. And really, when you configure AIGP, you're going to have to do it for all routers in, or all BGP speaking routers in that network, really for the AIGP metric to make sense. So if we wanted to run AIGP throughout the entire autonomous system, so say this was just AS4, just for example, we would have to configure AIGP to be running here, on here, on here, this router here, and you get the point, and even on the routers down here. Really, to have the AIGP overall total metric accumulated across the entire network. And just like local preference, to configure AIGP, it's incredibly easy. It's even more straightforward to actually configure than local preference, because with local preference we needed a route filter via a policy statement, or we could just do it on the group itself. This is even more straightforward. So what I've done is I've just logged onto R3, which is the router which I've just circled in red, so just so you can see where we are. And let's do edit protocols BGP group internal AS1. I'm doing internal because, as you can see, R3 doesn't have any connections to ISP2 or ISP3, which is covered by the COI box, but it doesn't matter because the configuration, the syntax is exactly the same, whether it be eBGP or iBGP. But again, you would have to configure this for all routers in that same autonomous system and for those routers in those other autonomous systems as well. And to configure it, it's very straightforward. We are going to do set family, if I hit question mark, iNet, hit question mark again, and we're going to do labeled unicast, hit question mark right at the top, just about here. We've got AIGP, allow sending and receiving of AIGP attribute. So let's do AIGP. And now if I do quick show, and there we go, right there, we can actually see for BGP group internal, we have got family iNet labeled unicast AIGP. Now let's actually just talk what that labeled unicast actually means. What labeled unicast means is that we are taking the OSPF v2 or IPv4 metric from the routing table and we are injecting it into BGP. That's basically it. What I could also do, if I just go up a level, you can now see I'm just in the edit protocols branch. I'm not in a specific group. I could have done that command at the BGP level. So I could do set family iNet labeled unicast AIGP. And now if I do a show, we can see it's configured still for the internal AS1, but it's now configured at the overall BGP protocol level. So if I was to enter in another group, so say we actually built a connection between these different service provider networks, if I was to create a group which was external, that would then inherit this information because it is coming from here in the first place. So that is how you can configure AIGP and what AIGP actually is. It is a very niche and specific use case, but that's essentially what it is. But you might be asking yourself, well, hang on, Dave, what about local preference that you spent most of this video actually talking about? What you've got to remember with the BGP path attributes is that router is basing its routing decision on which attribute wins, i.e. where is that tiebreaker. Now for local preference, if those values are the same, get to that same destination, it will then move on to that next step, which would be in the Junos world AIGP. But what you really have to remember is that for local preference, it is internal to that network itself. It's internal to that autonomous system. For AIGP, it is in between autonomous systems themselves. Yes, you could still do it inside an autonomous system, but it's also designed, AIGP, for use between autonomous systems because, coming back to my example, all of this was the same great big network, the same great big autonomous system. And there we go, everybody. That is the end of this video. I hope you found that informative. I hope you found that useful. As always, we go through a lot of information, and what we covered on this video was the BGP path selection process in the Junos world, how it goes from the top to the bottom, what are those tiebreakers, and in some cases, what are the actual values. And then we started to concentrate on what is local preference, what does it do, how can we influence or manipulate that within an autonomous system itself. And then we moved on to AIGP, or Accumulated Interior Gateway Protocol. So as you can see, there's a lot more attributes we've got to go through, so please stay tuned. So if you like this video, please subscribe so you can stay up to date with all the latest and greatest videos that I release weekly. In addition, please let me know any questions or comments that you may have. Other than that, thanks for watching and goodbye.